Our fourth video on motion will cover freefall motion. A body that is freely falling or free-falling will undergo a constant acceleration. In a vacuum, all objects will fall at the same rate. In air, objects that are falling encounter air resistance. If you drop a feather and a hammer in air, the hammer is going to hit the ground first. However, if you drop a feather and a hammer in a vacuum, they will fall at the same rate, so they will hit the ground at exactly the same time. The same thing is true, say, on the moon, where there is no atmosphere. Objects will fall at the same rate. This rate that all of these objects are falling at is the acceleration due to gravity, which can also be thought of as the acceleration of a freely falling body. Acceleration due to gravity is represented by the letter G for gravity, where A, acceleration, equals gravity. On Earth, the acceleration due to gravity, G, is 9.80 meters per second squared, or 32.2 feet per second squared, depending on which system our other units are in. As I just mentioned, these are the values for Earth. If you are on the moon or another planet, the acceleration due to gravity will be different. It will be much less on the moon, but it will be much greater on Jupiter. In our class, we only need to worry about the value for Earth. Let's take a look at an example of freefall motion. A baseball is thrown vertically upward with an initial velocity of 20 meters per second. How high does it go? How long does it take to reach its maximum height? And how long is it in flight? Let's break this problem down and look at the first question, how high does it go? In order to solve this, let's first define which direction is positive and which is negative. A lot of times we will define positive as down, so the acceleration due to gravity will be a positive number. Next, let's write down everything we are given. We know the acceleration due to gravity is 9.80 meters per second squared, since the other units we see in this problem is metric. This will be a positive number because we defined down to be positive. The initial velocity will be negative 20 meters per second. The initial velocity is negative because it is moving up, which is defined to be negative. The final velocity is 0 meters per second because there is a moment of time when the ball is at its maximum height that it's not moving. We are trying to find the distance s. The only equation that includes acceleration, initial and final velocity, and distance is the basic equation of 2as equals v sub f squared minus v sub I squared. We will need to rearrange this equation to solve for the working equation written in terms of s. In order to get s by itself, we will need to divide both sides by 2a. This leaves us with a working equation of s equals v sub f squared minus v sub I squared divided by 2a. Next, we can substitute and see that we have 0 squared minus a negative 20 meters per second squared divided by 2 times 9.8 meters per second squared. When we square the negative 20, we end up with positive 400 meters squared per second squared. Dividing and canceling off unwanted units, we end up with a distance of negative 20.4 meters. Our answer is negative because the ball was thrown vertically up. The next part of this question asks how long does it take to reach its maximum height? Even though we just wrote down all of the information we were given in the last part of the problem, we will need to write it down again. The acceleration is the acceleration due to gravity, g, which equals 9.8 meters per second squared. Initial velocity, or v sub I, is negative 20 meters per second, and the final velocity, v sub f, is 0 meters per second. We are trying to find time in this part. Next, we need to find a basic equation that includes a, vi, vf, and t. The basic equation we are looking for is v sub f is equal to v sub I plus a times t. We need to rearrange this to find our working equation written in terms of t. To solve for t, subtract vi and then divide both sides by a. It might be helpful to write down how you solve for t. This gives us a working equation of t equals v sub f minus v sub I divided by a. Last, we can substitute in the given data and see that t is equal to 0 minus negative 20 meters per second divided by 9.8 meters per second squared. This gives us a time of 2.04 seconds rounded to 3 significant digits. The last part of this question is how long is the ball in flight? This is more of a conceptual question. The ball decelerates on the way down and accelerates on the way up at the same rate. This is because acceleration in both directions is the acceleration due to gravity, since it is a constant. Since it takes 2.04 seconds for the ball to reach the maximum height, it will take an additional 2.04 seconds for the ball to fall back down, since the only force affecting the ball is gravity. Therefore, it will take 2.04 times 2, or 4.08 seconds for the ball to reach the ground. We can also talk about what speed the ball will hit the ground at. It will hit the ground with the same speed as what it was initially thrown at, because again the only force acting on the ball is the acceleration due to gravity. Therefore, the ball will hit the ground at 20 meters per second. This concludes our discussion and examples of free falling motion.